Thank you all for joining. This is such a pleasure to be here. Last year when Nitish and I were in the audience, we were thinking it would be so cool to get a chance to present here, and finally it's happening. So thanks a lot, Adrian, for giving us that opportunity. Just want to talk about three things here: safety, and how we should take care of that when we deploy foundation models at scale. So first, about who we are. We both are co-founders, worked at Apple SPG for maybe 6-7 years. And around 2021, we started building this company to do bike lane delivery robots. And I want to take this opportunity to thank some of our founding engineers. Some of them are in the audience, Arul Gupta, for being the bedrock of our startup. And we were acquired around a month back, and we are super excited about it. Rajesh is here. He gave us such a tough battle to pass the acquisition benchmark, so thank you for that. And looking forward to scale our technology to more than 2,000 robots pretty soon. So why did they acquire us? That's the key question. So there are two key things that we have. One is a Plenoptic sensor, which closes the gap between a LiDAR and a camera system. LiDARs are super expensive, were super expensive when we got started. Cameras have lower coverage in darkness and also when you have sun glare. So we built a new sensor which is based on polarization imaging. And this gives us an advantage because when you look at unit economics of bike lane delivery robots, it's almost impossible to have a $1,000 sensor. So we were able to get this camera down to like $100. The next thing that we have is the simulator that Nitish will talk about. As you can see, it has a lot of hard corner cases that are being simulated. It's almost impossible to collect as a startup so much real-world data with so little time and money. So we used a simulator, and it automates the creation of hard scenarios. So how does this sensor? So first, I'll talk about the sensor and give you some idea about what it does. So we basically use the polarization state, which is the plane of oscillation of the electric field, and probe that to extract a lot of interesting properties which are usually not possible to be extracted by a camera or a LiDAR system. So as you can see here, the blue plane here is the electric field oscillation, and then we use some custom optics in front of the camera that you saw. And we have some standard CMOS image sensors from Sony, and we use transformers to get a dense depth map, a very high quality RGB image, shape of objects, and material properties. So here is a sample output of the sensor. So here you can see the depth image. It's a test done in our parking lot. Here is shape of objects. It's basically a shortcut for any occupancy. So you can see the curb, which is pretty hard to see using traditional sensors. We also get two other additional channels. One is the texture, and then the other one is the material property. And the performance, as you can see here, compares pretty well with the state of the art. This is probably used in most of the robots that you saw today. And one of the main reasons we wanted to use our sensor is it has very high resolution, lower false negatives, and very high depth accuracy. So that was the main reason we used this. Some of the advantages that I'll quickly go through. As you can see here, a person in a shadow in a tunnel is almost invisible with a 105 dB dynamic range HDR camera. But when you plot a property of the world which is not intensity or color, you're able to extract the contrast for the pedestrian. This is another example under nighttime. So you can see that when you have almost no light, a regular camera cannot see the pedestrian or the car or the lane marker, but our sensor was able to see it. This is another example where it performs very well under direct sunlight, where most of the cameras have issues. So these are some of the advantages. Now going into some challenging scenarios. So as I told you earlier, we extract texture of the world. So a bicyclist, which has very low contrast, is usually hard to pick up using a regular depth map. But using our sensor, since we extract a lot of texture of the person, we are able to get a good quality detection going. And yesterday we saw a lot of applications of humanoids. One of them is shown here. Like if you want to pick glass, it's usually very challenging. So we are able to get glass very good. And also small screws that you can see here with very low working distance. This is used for industrial applications. And also removal of glare on the floors. So this is also applicable for factory floors. So this is the guardrail system that we used to guarantee that we don't hit into anything. So we have a safe parallel system to prevent any collisions. And then we have a very intelligent foundation model, which is fully trained in simulation. Right? Yeah.
So the way we built our autonomous robot for driving in bike lanes was that we created a foundation model that can understand generally anything that it sees and can come up with a way to drive in that environment, complementing that with this guardrail system so that we can actually go and deploy this. So in order to build a foundation model, one of the first things we needed was a huge amount of data. And we had no way to collect that in the real world. We had a handful of robots, and there was no way we could actually go collect data from the perspective of our robots in the real world. So what we decided to do was use simulation and use the fact that visual encoders today that are trained on internet scale data are already really good and can bridge the gap between sim and real to a large extent. So what we really needed from the sim was diversity and to be able to create a huge amount of diversity at scale. So we built our simulation engine. We made it so that it can render really fast. It can do a lot of different, it can be realistic enough that sim to real transfer happens, but not hyper realistic so that it just takes forever to render. So we made that trade-off and built the simulator. What you can do is essentially you can randomly sample data from it. So you can randomly create a road network, randomly modify the lane graph and the various properties of the lanes, randomly create city blocks, randomly create vegetation in that city blocks, and then have your robot drive around in that environment. This whole thing is built so that it's not you don't have to create each town by hand. Go off and just specify a list of properties that you want to randomize, and then you have thousands of different towns being created and millions of miles of data being collected, essentially. So here you can see the lane graph is the same, but the different city blocks are being randomized. So you can go from dense urban areas to parks and suburban areas.
One of the things I wanted to add is this whole process takes maybe 10-15 minutes. Rajesh didn't believe us when we told him that, but he finally got it.
One of the things we really cared about was driving really well in bike lanes and the road margins. And bike lanes come in all sorts of flavors, so we had to randomize them, and then we came up with a recipe to do something like that. So you can just have different types of lane boundaries, with or without a buffer, with or without different types of markings on the left or the right, and different colors, and different types of all the variants that you could possibly think of, and then just have the randomization that help us create a lot of really hard driving data. And in addition to the assets and the procedural scenario generation, we are able to also do a lot of diverse scenarios and behaviors, so you can have a lot of interesting interactions with pedestrians, interesting interaction with other road users, like people on bicycles. So in this scene, you can see it going around trash cans, waiting for vehicles to pass, and being able to deal with all of this random. And we don't have to create any of these scenes by hand or orchestrate any of these things. It just all happens. You just click a button and you just get millions of miles of data. Very quickly. You can create interesting behaviors like this, for example, edging into traffic a little bit so that you can create a space for yourself and go around. So it's not just like very simple behaviors. You can create all sorts of complex behaviors. And the nice thing about this is that now that you have all this data, you have the simulation which can not only create random data that you just randomize a bunch of parameters and let it go, but you can also create rare interactions with road users. So for example, you can have an interaction where a person in a bicycle on a scooter cuts in front of the robot, but you can vary other other environments, like other properties of the environment, like change the lighting conditions, change the density of the traffic around the robot, and so on. So you create not just so if you were to try to collect this type of data in the real world, you could get one instance of it, and having that as part of your validation set tells you whether or not you solved that one instance. But having this in simulation really makes it possible for us to exhaustively vary all the factors of variation and then really test whether something has been solved or not. We can also combine that with real maps. So for example, we can take an OpenStreetMap, select any area from that, and then essentially create a virtual version of that in our simulator, and then randomize all the various properties of that map. So as a result of this, we are able to generate more than 200 miles per GPU per day. So just throw more GPUs at the problem, get more data with lots of interesting interactions happening. So this was the key data engine that helped us unlock this foundation model. And the way we trained it was basically, once you have simulation, giving you ground truth positions and behaviors of all the other agents, you have essentially an online teacher. So you can probe that teacher in a lot of interesting hard situations and essentially have this dagger-style learning. So we basically have a student agent that is taking images and other raw sensor data as input and is trying to output a bunch of different things. What is the right path, segmentation maps, depth maps, whatever you want, like as many outputs as you want from the student agent, you can extract those. And then you have the teacher agent that is looking at a different view of the world. It has access to the ground truth. It knows exactly where the other agents are, what they're going to be doing, and it can use all of that. And you can have a rule-based teacher agent or a RL-trained one that then outputs what we can consider ground truth supervision. And so we train this model in a dagger-style way. It goes off, makes a bunch of mistakes, ends up in like close encounters with other cars, hits obstacles, and so on. In all of these positions, we can then probe the teacher about what is the right thing to have done from there. And that's impossible to do with real data, almost impossible to do with real data. You will not be able to be near collision situations so often. And even then, like if you have your teleoperator drive out of them, you can only collect a handful of examples of really being able to recover from hard situations. But in Sim, we could do that at scale. And not only we have an online teacher, we can combine that with an inquisitive student. So we can have a training mechanism where the model is not just outputting the correct behavior, but can also be the same foundation model can be queried and be asked a question, hey, what if I took this other path? Why was that not the correct thing to do? And so the student can ask all of these questions, and the teacher can answer them because the teacher is has access to the internal state of the simulator, and it can answer all these questions, and it knows why that is not the correct thing. And that gives you so much valuable gradients that if that foundation model has to explain the correct behavior and answer all these questions and do segmentation and do depth estimation, then you're not basically overfitting on Sim anymore. That makes it transfer to the real world. So basically what we're able to do is train a policy in simulation, like what you see on the left, and transfer that to the real world. So here you're seeing the segmentation and depth output heads and how they transfer. So this model is trained purely in simulation, zero real data, and the performance on a validation set in Sim is on the left, and the validation set on real data is on the right. So essentially the lesson here for us was, if your visual encoders are trained on the entire internet and not fine-tuned on simulation, then you can basically work off of Sim data and transfer your behavior into the real world. And that was the perception heads, but then we can also have the path that the model is trying to output. So it can go around obstacles. For example, in this case, construction. This is another situation. There's a vehicle parked in the bike lane, and it has to go around these vehicles. It knows when to return back to the bike lane. It can deal with open, car doors opening and so on. Right. And the other thing that we are able to do is now that this entire foundation model is built off of attention blocks or transformer blocks in which the attention is traceable all the way from image patches to the model's output. So if the model is outputting a particular path like this one here, we can probe where the model paid attention to in this scene to come up with that path. And this is important because we are building these end-to-end models. If a model didn't do the right thing, it would be really hard for us to understand why it didn't do the right thing. Like, did it not pay attention to the right thing? Was it not there in the training set, or what's going on? So having these model introspection tools really made it possible for us to iterate faster and understand why something was not working. So in this case, we can see the model is choosing to pay attention to the lane boundary, the car on the right, and it's also looking at that car on the left. Here's another situation. There's a lot more complicated. There's a weird construction vehicle on the left, and it still has to figure out the right path. This is another iteration of our model where on the left you see the model's output. So it's outputting a left lane boundary, a right lane boundary, and the path it wants to follow. And the red dot is basically where it wants to come to a stop. And we traced the attention map of that red dot to say, like, why do you want to stop there? And it paid, and the attention map clearly tells us, look, it's looking for that stop sign. It's looking at that stop sign. It's looking at the road marking. Like, those are the two big red things that you see. It's paying the most attention there. And it can, so essentially the model has learned to become a lane detector and a stop sign detector, and we didn't have to teach it any of these things. We just trained it on a whole bunch of data in simulation. I can understand those, where to pay attention to do what. Here's another example. In this case, there's a person crossing the street, and now that those same weights of the network, the same attention mask is now becoming a person detector. So basically, we don't need person detectors. We don't need stop sign detectors, we don't need lane detectors. It just, the model can figure out what to do. Just have to throw like millions and millions of frames at it. And it not only works for this form factor of the robot that we had 6 cameras and like a delivery robot, we just took the same model weights, put it on a dog robot. So the camera is 1 foot from the ground, 30 centimeters instead of like almost 1 meter from the ground, and 1 camera instead of 6. And we just let it run, and it's able to generalize. So we can make the same model weights work on a different robot embodiment. Right. Thank you.
Thank you. Just want to end with one anecdote from Professor Jeff Hinton, who was Nitish's advisor and also our advisor. So we used to have weekly meetings with him. And during one meeting, we were talking about safety because our robot, we were doing a test in Old Palo Alto, and it veered off crazily to the left. And then the question he asked was, what is the stopping distance of the robot? And then we were like, maybe 0.5 meters. Why don't you put a whisker on the robot? Because cats have whiskers, and that's one of the reasons why we thought of a guardrail system, which is very parallel to the end-to-end model. There was one more thing he said, which was basically when you're in a flight, a pilot, when they're learning how to fly a plane, if you want to know what you need to do when there is an engine failure, you can only do it in simulation and not in the real world. So that was like a seed for us to focus a lot more on simulation instead of real world data, because most of the real world data is boring. And you can't learn much from it. It's definitely necessary, but safety is also correlated with intelligence. So we focused a lot more on making our driver a lot more intelligent.
Yeah, most learning happens at the boundaries of the data distribution, and those boundaries are rare by definition in the real world. So,
thank you. We have maybe 2 minutes. If you have any questions, we can take it. Otherwise, thanks a lot for this opportunity.